Good afternoon, Khushi. Good afternoon to all of you guys. Prashant. Just wait for few minutes, 2-3 minutes more, then we will start. So, how are you doing, guys? I hope आप सभी का रिवीजन प्रिपरेशन ट्रैक पे चल रहा है. Every one of you is doing well with your preparations. Less than 30 days are remaining according to the calendar for your GATE exam. So, anyone is feeling butterflies or goosebumps? Yes. So, remember one thing, when you will discuss with your friends or whenever you will have conversation with your friends who are also preparing for GATE exam, you will think like these goosebumps and butterflies are calculator. Acha, main le aaya. Thank you. These butterflies and goosebumps are fear. But whenever you will discuss with me or anyone else who has some experience in this field, you will find these goosebumps and butterflies are just the excitement. Okay. So, have you received your admit cards yet? Means, are they available on the GATE website? No, not yet. Okay, wonderful. So, it's okay. They will provide. And remember, GATE exam is not going to postpone at any cost. Like if any one of you thinks or you find any information somewhere like due to COVID situation or blah 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 or Omicron or Florona or white fungus, yellow fungus, red fungus, pink fungus or any color of disease, GATE exam is not going to postpone. It will be on the same date. Okay. So just do your preparations. So let's start our discussion for the mass transfer quick revision classes. Here we are supposed to cover up the entire mass transfer including the basic concepts plus the equations, formulas, whatever we are going to use, the correlations and some important GATE previous year questions. And this week or maybe next week, means in 8 to 10 days maximum. Okay, we are not going to discuss the details of all the things, but obviously for some topics we will go in quite depth which are important or in the topics in which any one of you is having doubt. So it is not like the normal classes, the lecture which we used to have in during the classes, during the course, where we completed this subject in 40 plus hours, 50 plus hours, 60 plus hours. Here we will cover it in 8 to 10 days maximum. Okay. So before we start, my first question to all of you, you don't need to answer here. Okay. Just think in your mind, what is mass transfer? Okay, you don't need to answer on this portal, just think in your mind. If I need your answers here, I will mention. Okay, so what is mass transfer? And I hope every one of us know about this. Mass transfer is the net movement of molecules, or you can say mass, from one location to another location. Simple. Mass transfer you may define as the net movement of mass from one location to another. Simple. Okay, technically you can also say, if you want to explain this in details, net movement of mass from one location to another within the same phase or between the phases. Okay, like intraphases or interphases, you can say. So that is mass transfer. And here in our subject, we are concerned with that mass transfer which we want to observe. Okay, in this entire universe, mass transfer is taking place everywhere. Okay, but we are not concerned with all the mass transfers. We are concerned with only those mass transfer processes which we want to investigate, which we want to study, which we want to analyze. Okay, so next question is, what is the significance? What is the significance of doing the study about the mass transfer? In one word, if you can answer, any one of you. What is the significance? Why we are studying this subject? In one word, or maximum 2 words. If any one of you want to answer. That's absolutely correct, Prashant. Mass transfer, the main significance is to study the separation. Okay, separation processes. For separation of mixtures. So the net movement of mass from one location to another location leads us to separation of the mixtures. And what is separation? That is the next question. So separation is division. Okay, you can say division of a mixture or division of something into its constituents, into its elements. Okay, so here if we talk about the separation processes, we can say, what is separation process? Separation is the division of something into its elements, or you can say constituents. Okay, next is separation processes. So any process which leads to separation is called separation process. Okay, and separation process means any process which helps us to separate the mixture into its constituents, or at least to get a product which is enriched in one or more components. Okay, that is also a separation. Okay, it is not like we know the second law of thermodynamics, 100% efficiency is not possible everywhere. So similarly, we know that in separation, suppose we have a binary mixture of A and B, so it doesn't mean that we will get A, pure A. It is also possible that we get two different products. One is enriched in A and one is enriched in B. Okay, that is also a separation. Okay, so what are the separation techniques we use? So there are 5 separation techniques. I hope all of you remember. One is phase creation, second phase addition, third barrier, putting on some barrier, fourth is the force field, and last one is the with the help of solid agent. So I hope you remember all these things. Phase creation, can you write any example of this? What is phase creation? The example. I hope you know phase creation, where we introduce the feed to the system and we create some phases, a new phase in the system. Like we are sending the liquid feed and in the outlet we are getting two different phases. One is liquid, one is product, or one is solid, one is liquid, or two immiscible liquids or something like that. Okay, any example of this type of process can you mention? Yes, distillation, evaporation, these are the examples of phase creation. Correct. Wonderful guys, thank you. Next is phase addition. Phase addition is where we are adding, we are introducing a new phase to the system. Okay, like we are sending some feed to the system along with a new phase. Okay, or you can say some mass separation agent, MSA, mass separation agent. Okay, and we get two different streams or two different phases at the outlet. Okay, the example, any example? Here the example is distillation, one of the example. Here extraction, or you can say gas absorption, etc. Okay, correct. Leaching is also one example. Wonderful. Next is barrier. Barrier is what? We introduce the feed to a system where we pass the feed through some barrier, through some semi-permeable membrane or a filter medium, and we get two different products. Okay, like filtration or the membrane separation operations. I hope you remember. In membrane separation, there are several examples like nanofiltration, ultrafiltration, reverse osmosis, etc. Force field is where we introduce the feed through a force field and we get two different products, like electrolysis, where you introduce the water in the electric field and you get hydrogen and oxygen as the separation. Next is solid agent, where we introduce the feed to a system along with a solid and we get two different products. Okay, the example you know is the adsorption or ion exchange reagents, you can say adsorption or ion exchange processes. And although we know that ion exchange is kind of adsorption itself, but Yeah, we can mention that separately. So these are the separation techniques. Now the next point is modes of mass transfer. Okay. See, I don't know whether you guys are noting all these things. By the way, you are not supposed to note all this thing. You already know this. If any one of you is making some notes and anything, so you can ask me to pause, or you can later on you can watch the recording and make your notes if you wish. Okay. So because we want to cover up the entire mass transfer in less time. That is the meaning. Quick revision class. Quick. Okay. So just let me know if you have any other idea here. And yes, you are always free to ask your doubts. So what are the modes of mass transfer? Just mention the numbers. How many modes of mass transfer are there? 1, 2, 3, 4, 5, 8, 9, 10, 11, infinite. Correct. There are 2 modes of mass transfer. And can any one of you tell me on what basis we define these modes of mass transfer? On what basis we define these modes? Like you study the modes of heat transfer as well. So on what basis we do this discussion? We separate them. Like there are 3 modes of heat transfer: conduction, radiation and convection. Similarly, 2 modes of mass transfer are there: molecular diffusion and convective mass transfer. So on what basis we define them, we differentiate them? Correct, Prashant. In heat transfer, the modes of heat transfer we define based on the movement of molecules. There are 2 things, remember guys. One is microscopic analysis, microscopic parameters, and one is macroscopic parameter. Molecules are the microscopic parameters and medium is the macroscopic parameter. So in case of heat transfer, we define the modes of heat transfer based on movement of molecules. If molecules are stationary and heat transfer is taking place, that is conduction. If molecules are moving and heat transfer is taking place, that is convection. And if no molecules are present, still the heat transfer is taking place, then that is radiation. And I hope you know that for radiation, for radiative heat transfer, medium is present or does not present, we don't care about that. Okay. Like sunlight travels in vacuum, and here on earth radiation occurs in everybody. If you know the which law is there, I guess Kirchhoff law was there, or maybe I don't remember the name in heat transfer, sorry, but there was some law which states that every body emits some heat energy, some radiation. Okay, so I hope you remember which law was there in heat transfer. What is the name which states that every body emits some radiative heat energy? Kirchhoff law or Stephen Boltzmann law, I don't know. There are so many laws in heat transfer. Any one of you can help in that? Although this is mass transfer quick revision classes, but I believe you have revised your heat transfer part as well. So any one of you? No? In heat transfer radiation? Which law suggests or states that every body emits some radiation? No, कोई बात नहीं. So all of us are on the same page. It's good and bad as well. Leave it. So here on the earth, like if everybody is emitting some heat and radiation heat energy, so air is the medium, so still radiation is taking place. So there are so many things, you know. Okay, but in mass transfer, if medium is stationary, then molecular diffusion, and if medium is in motion, then it is convective mass transfer. And further we can derive this convective mass transfer into two categories. One is natural convection, second is forced convection. So before we talk about other things, I have one simple question to all of you, because I assume that you have studied your mass transfer, you have done your mass transfer from your side as well. That's why you are here in quick revision classes. Okay, that is just my assumption. So I'm free to ask the questions. Suppose we have two beakers of water. In first beaker, and this is the second. In first beaker we have kept the sugar particle, sugar cube, or the sphere, you can say, on the top of the surface in the bulk, and in second container we have kept it at the depth of the container. Okay, so out of these two, in which mode the dissolution of sugar will be fast? In which container the dissolution of sugar will be fast? First one. Thank you guys for your response. So that's correct. Why? Because of the natural convection, we can say. If we assume that this water is stationary in the beaker and no external force is acting on this other than the gravity, okay, so what will happen here in this case? The sugar molecules will dissolve in water and the liquid film around this sugar particle will be highly concentrated. And here at the bottom we have low concentration. Concentration of what? Of sugar. High concentration of sugar, low concentration of sugar. And because of the high concentration, here the density will be high at the top, and here at the bottom density will be low. Okay, and we know that in case of liquids, whenever there is a density difference, flow currents will start. So the water will start to flow like this. The high dense water will be at the bottom, low dense water will be at the top. So flow currents started, means convective mass transfer has a start. So diffusion plus convective mass transfer is there. But in this case, at the bottom we have high concentration, high density, at the top we have low density. And since density is already high at the bottom, so high dense molecules, high dense liquid will not go at the top. Okay, that is not possible. So no convection is there. That's why in first case dissolution of dissolution of sugar will be high, fast. Okay, I believe that all of you were having the same reason and explanation with you. So anyways, so here this natural convection occurs due to the density difference, delta rho, and forced convection due to the pressure difference, okay, or due to some momentum transfer. So that's why it is also known as bulk motion of fluid. Bulk motion of fluid or bulk flow. Okay, like with the help of centrifugal pump or with the help of compressors or anything, we are transporting the fluid. So that is the modes of mass transfer. And I believe all of you remember that for mass transfer to occur, two things are required. First is the mass transfer resistance, it's the most important one, and second is the mass transfer driving force. Okay, so mass transfer resistance is the most important part, and the reciprocal of mass transfer resistance is called mass transfer affinity, you can say, and in different processes it is known by different terms, like whenever mass transfer is occurring through the turbulent flow, reciprocal of mass transfer resistance is known as mass transfer coefficient. Whenever mass transfer is taking place in laminar flow or within the same phase, so reciprocal of mass transfer resistance is known as diffusivity, the diffusion coefficient. I hope all of you know that. And when we are talking about the dissolution of solute in the solvents, then the reciprocal of mass transfer resistance is called its solubility. Okay, so I hope you remember all these things. So we will discuss first the molecular diffusion, then we will move ahead. So today's in first lecture we will talk about the diffusion. We will try to cover up the entire diffusion part. So before we talk about the molecular diffusion and other things related to this topic, try to recall the definition of diffusion in your mind. What is molecular diffusion? If anyone asks you, suppose this today you have interview and anyone is asking, what is molecular diffusion? So how you are going to answer? So I hope you have your answer, and that is same which I have written. Molecular diffusion may defined as the transport of molecules from high concentration region to low concentration region within the same phase. That is most important line. Within the same phase. Remember, diffusion cannot occur between the phases. Diffusion always occurs within the same phase. Okay. Although later on we will see interphase mass transfer and other things, but there between we have two or more phases, so diffusion in all those phases will be different. Okay, you cannot combine the diffusion of two phases. Remember this. Diffusion always occurs within the same phase. Okay, so that is molecular diffusion, and in molecular diffusion, if we talk about this further, so molecular diffusion we can explain, we can study with the help of Fick's first law of diffusion. Fick's first law of molecular diffusion. So again, try to recall its statement. What is Fick's first law of molecular diffusion? Fick's first law of molecular diffusion states that the flux of some species with respect to the observer molecular diffusion, Fick's first law of molecular diffusion, the statement is the molar flux of some species with respect to the observer moving with molar average velocity of the medium is directly proportional to the concentration gradient of same species in the given direction, in the same direction. Okay, like if there is a medium flowing in z direction, suppose, and there are n number of molecules. This is molecule A. Some molecules are also there, some other molecules B, C, D, and so on. Okay, so the molar flux of component A with respect to the observer moving with molar average velocity. So I hope you remember we defined the flux, we discussed that, and flux can be defined in three ways. The molar flux with respect to, I am talking about the molar flux with respect to stationary observer, defined and denoted by Na. The molar flux with respect to observer moving with mass average velocity, which is denoted by small u, is capital Ia for component A, and the molar flux with respect to the observer moving with molar average velocity, that is denoted by capital V, is denoted by capital J. Here we are talking about the molar flux of component A, some species, let's say component A, with respect to the observer moving with molar average velocity in some direction is directly proportional to its concentration gradient in the same direction, Z. How the dCA by dZ means how the concentration is changing along the Z direction. That is the meaning of gradient. I hope all of you know this. Okay. So when you will expand this expression and try to remove this proportionality sign, here you will get DAB if we have a binary mixture like this. Okay, and remember, flux, the rate of mass transfer, rate of any process cannot be negative, it has to be positive always. And if we talk about the concentration gradient, so that means the final change in concentration means final concentration minus initial concentration. And as we know, mass transfer always occurs from high concentration to low concentration. Means mass transfer is taking place from initial state to final state. So here the concentration must be high. And in final state concentration has to be a low concentration, must be. Okay, so this difference will be a negative value, and since the rate, the flux cannot be negative, they have to be a positive quantity, so that to compensate the negative value of dCA, we put one minus sign here. So I hope it is clear to you what is the definition and what is the meaning of all these terms in Fick's first law of diffusion. And DAB, if you want to define, you can say diffusivity, also known as diffusion coefficient, of component A in a mixture of component A and B. Okay. Means if I write some diffusion coefficient like this, Dij, what is the meaning? The meaning is diffusivity of component I in a mixture of I and J. So the first notation is always the diffusivity of that component, which is coming first, and the second component means mixture of these two. Okay, I hope it is clear. Is it clear, guys? The explanation, the meaning of Fick's first law of diffusion, the notations, why we are having negative sign here, what is diffusivity, what is concentration gradient, and what is this flux? Is it clear to all of you? Okay, wonderful. So, do we need to explain these things again? What is the meaning of stationary observer, moving observer with U, moving observer with V, or is it clear? Okay, if you think we need to discuss, write discuss, and if you think we can skip this, you are already comfortable, so just mention skip. We will move ahead. The flux and different type of flux and all these notations. Skip. Okay, so all of you want to skip this. Okay, I mean, so that means all of you are comfortable with that part. Wonderful. Remember, again, here one thing. What is flux? I am not asking mass flux or molar flux or heat flux or momentum flux or any flux. I am just saying flux in general. What is flux? How will you define? Recall in your mind. Don't need to answer here. So flux is the transportation of any quantity per unit area, per unit time, normal to the direction of transport. That is important. Okay. Quantity per unit area, per unit time, and which area? Area normal to the direction of transport. Okay. So tell me one thing. If I say direction of transport is x, some quantity is getting transported in x direction, so where we will define the flux, in which plane or on which axis we will define the flux. Like suppose flux is q. So here in suffix I will write, what I have to write. If transportation is taking place in x direction, then q is the flux here, suppose some quantity flux. So in suffix of q, what I have to write, in which plane or which axis, like qz, qy, qx, qxi, qzx or qyz, what we have to mention. As you said, it is clear to all of you, already know. So I believe it will not be a difficult task for all of you to mention this. Correct, Varsha. Correct, Shankar. Flux is any quantity getting transported per unit time, per unit area, normal to the direction of transport. So we have three axes, x, y, z. I hope all of you know that. So if x is the direction of transport, so which plane, area means plane, which plane will be normal to this direction? YZ plane. So here we will write YZ, or you can say ZY, doesn't matter. Okay, QX we will not write. I hope it is clear to all of you. Whenever we are defining flux, and I hope you know what is flux. Okay. So these are the small things. Remember. Okay. No worry if we got it wrong this time. But I believe on all of you that if I ask the same question on 10 occasions, so at least on 9 occasions you will answer correct. And this was that 10th occasion where we were wrong. So it's a rare thing. Don't worry. Okay. Anyways, so wonderful. Now tell me one thing. I have one question to all of you. Just a second, huh? What was the question? Not bad. Before we move ahead, this is the question 100. Okay, question number 100. So can you answer this? C, that's correct. If you are saying C, that's the correct answer. Suppose this is some plane where the mass transfer is taking place like this, and the thickness of this plane differential element is dz. Okay, so I believe all of you know the law of conservation of mass, and the application of that law of conservation of mass, the application is material balance. So what is general mass balance equation? Rate of mass in minus rate of mass out equal to rate of mass accumulation. And usually at steady state the accumulation is zero. Not always, but usually. Okay. So here as well we can say at steady state accumulation is zero. So the mass balance equation will be rate of mass in equal to rate of mass out. Okay, and what is mass flux? If I say mass flux, suppose, so that is NA with respect to some stationary observer. Units will be, what will be the unit? Anyone? Remember in your mind. Units will be kg per meter square per second in SI system. Okay. Remember, whenever anyone is asking units, try to answer in SI system. Always. Until and unless they are not asking some specific ones. Okay. So here. So if I multiply this by area, it will become kg per second. That is the rate of mass transfer. I hope all of you know. So can you tell me what is this area? The cross sectional area, the surface area, or what? Which area? What is this area? Means which area? Like if you have to write some formula, so which formula you will write? The formula of cross sectional area, the formula of surface area, or the formula of some other area? This is the area of mass transfer. Okay. Correct. Cross sectional area, that's the correct answer. But remember, this is the area of mass transfer. And which area? The area that is normal to the direction of transport. So here the transport is taking place in this direction. So area normal to this direction is this. Okay. So let's say that is A. So when you will expand this expression, so rate of mass in, you can say the flux into area of mass transfer, which is normal to the direction, this area at z point, let's say this is some point z, so this point must be z plus dz. Or we can also write it as Na into A at z plus dz minus Na into A at z equal to 0. Now here if you divide it by dz on both sides, you can still write it as Na into A at z plus dz minus Na into A at z over dz equal to 0, as 0 over anything will be 0. And from first principle of derivation, you can also write it as d over dz of Na into A, that is equal to 0. And if you integrate this or try to solve, you will get Na into A equal to some constant. Here this is the area normal to the direction of transport, remember, because Na into A is rate of mass flux, and this is rate, Na bar. Okay, if it is molar flux, it will be molar rate of A. If it is mass flux, it will be mass rate of A. Okay, mass flow rate. I hope it is clear to all of you. So based on this, you can see Na will be inversely proportional to A. A is the area normal to the direction of transport. Okay, so if A is low, Na will be high, and if A is high, Na will be low. So here in this question, the storage vessel is there, vent is there, vent valve, and I hope all of you can understand this. This is some storage vessel, this is the vent valve, let's say. So we can easily see that the mass transfer will occur in this direction. So area normal to this direction is this. So here area of vent is low, that's why the flux will be high with respect to tank. So that's why the flux at a steady state condition, the flux will be maximum at the vent, option C. So I hope it is clear to all of you. Dhrumil, good question. We will discuss. Don't worry. We will come to that. I have those questions in my pocket today. Anyways, I hope this part is clear to all of you. Okay. So what is a steady state mass transfer? And remember guys, here you can see the flux will be constant always, and the rate will be constant always. So can you tell me which out of these two, first and second, which statement will be true? 1, 2, both, or neither of them? Correct. Second one. As flux is depends on area. If mass transfer is taking place through uniform area, only then we can say flux will be constant. Always. But if mass transfer is taking place through non-uniform area or the variable area, then the flux will not be constant, but the rate of mass transfer will be constant always at a steady state. Okay, and the same thing you must have seen in heat transfer as well. Like in heat transfer, there is a chapter called conduction. In conduction, there is a topic called heat transfer, the conduction through composite walls. Okay, I guess you have seen that, the conduction through composite walls. There they have different walls like this. Heat transfer is taking place and different conductivities are there, and you have to answer something. So you must know, like heat flux will be uniform or heat transfer rate will be uniform at a steady state, and based on that logic we solve this type of problems. I hope you remember that thing. So these are the similar things. It is always valid for everywhere, not for the mass transfer, but at a steady state in momentum transfer, at a steady state in heat transfer as well. So remember this. Okay. So I hope these things are clear to all of you guys. Now let's move to the next part. The flux equation. What is flux equation? Okay, what equation is called flux equation? You don't need to mention here, just recall in your mind. अरे क्या हो गया भाई, मान जा. So these are the three equations, 1, 2, 3. First equation, valid or not? Yes or no? Comma, two blanks, answer like this. Here, it is valid, first equation, yes or no? Fill your mark, and then comma, valid for what? Gas, liquid, or gas or liquid. So, for the first equation, filling the blank. Yes and liquid, correct. For the second equation, valid or not, and for what? Gas or liquid? Yes, correct. And what about the third equation? Valid or not, and for what? Liquid or gas? Why not valid? Because these are the molar flux. Molar flux of A with respect to stationary observer, molar flux of A with respect to moving observer having molar average velocity. NT is the total molar flux with respect to stationary observer. This is the mass fraction. But if I write this equation as this, then is it valid or not? Yes, correct. Whew. So now I am feeling good. Thank you guys for answering this. So means you have improved and you have worked good in units and dimensions and all these stuff. So thank you. That's the correct answer. Mass, mole, mass. And this will be valid for liquid as well as gas. Okay, depends for which phase you are defining that mass fraction. Okay, because we haven't seen anything like, we know that for the mole fraction, for liquids we define mole fraction usually in x, and for gases usually by small y, and the mass fraction by small w for liquid as well as gas. Okay, so this is the simple thing. So that's good to know, all of you know that this. And here this is the flux due to molecular diffusion. This is the flux due to bulk motion. Okay. So now steady state diffusion of A through non-diffusing B in a binary mixture, and this is steady state diffusion of A through stagnant B. Okay, let's say this is first, this is second. I am giving you two options, A and B, and try to match them, 1A, 2B, 1B, 2A, like that. Option A, this is some test tube filled with some liquid A. This is some medium B. Option B, this is some liquid mixture of A and B. This is some medium having component B. Medium of pure B, medium have B as well as some other components. So can you match it? I know all of you remember this, that mathematical equations are same, but these are two different cases. If we see the physical significance, can you do the matchmaking? We will discuss obviously. Like 1A 2B or 2B 1A, like this, or 1B 2A, ऐसे कुछ. What will be the answer? There are multiple components in this medium, B, C, Z, and in first option A, only B is there. The purpose is just I want to confirm whether you know the difference between these two, physical significance. What is the difference physically? Okay. See, steady state diffusion of component A through the stagnant B or stagnant film of any component B means Like we have a mixture of two components A and B, and only one component A is diffusing in air. This is air, only one component is diffusing, second component is not diffusing. So it means, just try to understand, just try to go in the depth. Here A and B, these components are there. This is air, this is liquid. Just try to understand like that. You know that vapor pressure concept. So vapors will be there, vapors of component A, vapors of component B will be there, but only component A will move, B will stay here only, B will not move. So this is the diffusion of A through stagnant layer of B. Sorry, मैंने गलत बोल दिया शायद. This is the diffusion of A through non-diffusing B. Just try to catch the meaning of each word. Diffusion of A through non-diffusing B. So B is there, A is there, but B is non-diffusing. A is diffusing it through that. Okay. Any example of this type of diffusion can you mention? The liquid extraction, you can say. Gas absorption, you can say. Okay. In gas absorption, we have the gas mixture having solute A plus carrier gas. Let's say A is the solute, carrier gas is B. So only A go in the liquid. Carrier gas component B does not go in the liquid. So diffusion of A through non-diffusing B. Okay, that is the answer. So for first, B is the answer. Okay. For second, diffusion of A through stagnant B is like in your room, you just spilled some water on the ground and water is evaporating in air, or there is a glass in which water is there and water is evaporating in air. Air is not going and dissolving in water, only water is going in air. Air is not getting dissolved in water, but water is going in air. So through stagnant layers of B, so 2A. Is it clear, or still you have any doubt? Mathematical equations are same, everything is same, but when we talk about the physical significance, there is a difference. Through stagnant B is basically the evaporation, you can say, evaporation of water in air, drying of clothes. Okay, moisture is getting vaporized from the wet solid and going in the air. Air is not going in moisture or solid, but moisture is going in air. So it's through stagnant B. But non-diffusing B means we have a mixture of two components, but only one component is diffusing, second is not. Is it clear, guys? Only one answer is there. Like gas absorption. Carrier gas A, solute A, carrier gas B, diffusing in liquid. B is not going in the liquid, only A is going. So diffusion of A through non-diffusing B. Okay, so mathematical equations are same, but meaning is this. I hope it is clear to all of you now. Physically, if anyone asks you in interview or anywhere, what is the difference? Differentiate these two conditions physically, or give the example. So we should be clear in our mind that what example we have to mention. Okay, liquid extraction is the example of this non-diffusing B. Gas absorption is the example of this. Distillation also you can say up to some extent is the example. No, distillation is not the example, because in distillation the idea is component A leaving the liquid phase, going in vapor phase, and component B is leaving the vapor phase and going in the liquid phase. So distillation is the example of counter diffusion. Okay. Yes. Now there are two terms again. If I ask you, one is equimolar counter diffusion, and one is only counter diffusion. I hope you understand the difference in these two. Process will be same, phenomena will be same, but the mass transfer rate will be different. Yes or no? Like if I talk about the flux equation, for the first case, what will be the flux equation? For binary mixtures, obviously. Of A and B. This is original flux equation in general. XA, YA doesn't matter. So here and here, flux equation we can reduce like what? What will be the flux equation here? Final form of flux equation. I am not asking the things only in these variables. Only in terms of these variables, what will be the final form of flux equation here for EMCD, equimolar counter diffusion? And for second case, for counter diffusion, correct guys, very well, Shankar, Prashant, Swapnil, Khushi. But for the second case, what will be the form of flux equation? Final form, in terms of these variables only. I am not going asking you the derivation. Okay, in driving force, no, but only in these terms. Tell me one thing, can we say this? Can we, for counter diffusion, can we write Na equal to minus Nb? Yes or no? Simply, just say that. No, obviously, we cannot write like that. Okay, so what will be the final form? Final form will remain like as it is. Okay, so now the question is, if you remember, I hope these two things are clear to you. So can you tell me, in case of distillation, vapor liquid equilibrium is there, we introduce the binary mixture of A and B in liquid form in the distillation column, where we are supposed to get liquid and vapor, vapor at the top, liquid at the bottom, all these things. You know what is distillation. I am not going in those details. I am just asking one thing. If McCabe-Thiele method, if you remember the McCabe-Thiele method, McCabe-Thiele or McCabe-Smith, कौन सा method है यार? What is that method in distillation to find out the number of ideal stages? Sorry, I forgot. There are so many things. Can you help me? McCabe-Thiele method. Yes. Thank you, Prashant. Thank you, Shankar. Thank you, Dhamil. McCabe-Thiele method. So, according to if McCabe-Thiele method is valid, applicable, so which diffusion will be there? This one or this one? EMCD or CD? Just like that. Okay. In short, you can say CD, EMCD. If McCabe-Thiele method is there, applicable. Macapthile method, the first assumption was CMO, constant molar overflow. Constant molar overflow means the flow rate of vapors, the flow rate of liquid in each respective section will remain constant at all stages. Okay, so if we talk about the rectifying section, so for first stage, second stage, third stage, all these vapor flow rate, liquid flow rate will remain same. Okay, so how it will be possible? It will be possible only, as we know, on each stage mass transfer is taking place. The idea is A is going from liquid to vapor and B is going from vapor to liquid. If A is more volatile, if A is more volatile, that was the idea. I hope you remember this. Okay, I'm going little fast because I assume all of you know all this thing. If any one of you have problem, you can mention. Don't think about anyone else कि मैं अब ये ऐसा कोई doubt पूछूंगा तो बाकी लोग क्या सोचेंगे. Don't think about anyone else. Now only less than 30 days are remaining. Think about yourself only. Be selfish. Ask anything, whatever you have. Okay. So idea is A is supposed to go from liquid to vapor. B is supposed to go from vapor to liquid. Constant molar overflow means flow rate of vapors, flow rate of liquid will remain same on all stages in the rectifying section and in a stripping section as well. So here if vapor flow rate is same, mass transfer is taking place on each stage. That means if 3 moles of A are going from liquid to vapor, then simultaneously 3 moles of B will come from vapor to liquid. Only then the molar flow rates will remain same. I hope you are understanding my point. Okay, so EMCD, if Macapthile method is applicable, first EMCD will be there. Okay, I hope it is clear. On the other hand, if I talk about this assumption that EMO is not there, constant molar overflow is not there. Okay, so that means in rectifying section, the flow rate of vapors, the flow rate of liquid is changing on each stage. And if flow rate of vapors, flow rate of liquid is changing on each stage, that means only counter diffusion is there. Means if 3 moles of A are going from liquid to vapor, then less than 3 or more than 3 moles of B are coming from vapor to liquid. Not equal. That's why the total flow rates are different. Is it clear to all of you? Hello? So these are the very basic things. All of us have studied all these things. Okay, we already know all these things, but it just that how we can apply these concepts and these things in every process. Okay, so that's what we are trying to do. Okay, that's what we will do in this quick revision classes. So trust me guys, if we do discussion like this and if you have any question like this in your mind, so you can also mention. It will help all of us. Okay, because ultimately like this way we will be able to clear our concepts, we will be able to execute our concepts on different practical examples in day-to-day life activities. So our interview preparation will also go side by side. Okay, so we don't need to prepare any extra. And even in GATE exam, if multiple select questions are there, so you know multiple select questions means 4 or 5 options will be there, 2, 3, 4, all the 5 options could be correct. So that's how, if we think like this, so that's how we will be able to answer those things. So that's why I am trying to do discussion with such methods. So anyways, so I hope we are clear with all this thing, the equimolar and counter diffusion, and their equation I don't think we need to discuss, all of you already know that. Okay, like if we need to write for gases, let's draw a table, let's try to draw a table. Okay, for liquids, थोड़ा और जगह दे देते हैं यहाँ पे हमें. So at a steady state, okay, for gases, what is the equation? Try to recall in your mind, then we will write. Okay, final equation. अरे क्या कर रहा हूं मैं, सॉरी, for EMCD, for EMCD case, sorry guys, to try to recall your equations, and for liquid it will be and second is for DND at a steady state, diffusion of A through non-diffusing B or diffusion of A through stagnant B, doesn't matter, mathematically the equations will be same. I'm not going to do the derivation. If you want it, so mention that, but that's not important. And if there is any problem in the equations, or you think these are incorrect or something, you can help me. And for liquids, I hope all of you remember, C average means molar density, average molar density, where average molar density you can calculate by calculating molar density at point 1 and molar density at point 2 and their arithmetic mean. Are these equations correct? Yes. Okay, wonderful. Okay, so guys, this is something regarding the diffusion. Okay, only two things are remaining, and if you are comfortable with the variables and the interconversion of the variables, like how to change concentration into partial pressure, how to change partial pressure into mole fractions, all these things, so you can change these equations into n number of forms, okay, based on the values of driving force given. Like driving force is given in terms of mole fraction or mass fraction or concentration or partial pressure, you can change these equations. I hope you know all those interconversions, those are not a big deal, okay. The last thing here is for D and D, diffusion of A through a sphere. Okay, like if we have a spherical ball and this ball is getting diffused in liquid, or you can say air, okay. So the distance of the radius of this sphere is, let's say, r1. This is the bulk medium where the diffusion is taking place. So radial direction, the radial distance is small r, and here is some point 2. This is the surface of a sphere, point 1. Here at the surface, the distance from the center of a sphere is r2, you can say, and here the partial pressure is PA2. At the surface, the radius is r1 from the center and the partial pressure will be PA1. Okay. The question is, why we are, if this is solid sphere, then why we are using the term partial pressure? Because partial pressure is the term associated with gas. Then why for the solids we are using the term partial pressure? You don't need to answer this, just mention yes or no if you know the reason. Okay, if you know the reason, yes. If you don't know the reason, no. Okay, don't explain, just mention yes or no whether you know this reason or not. Why we are mentioning partial pressure at point 1, although this is solid. Yes, okay, wonderful. So all of you know that. So still I am repeating, how the diffusion takes place. See, we have already mentioned diffusion always takes place from a high concentration region to low concentration region within the same phase. Okay, not between the phases. This is solid, this is air. Let's say, suppose naphthalene ball is present in the room, that is solid, getting diffused in the air, gas. So two different phases are there. Then still we are talking about the diffusion, and still we are talking about the partial pressure, because this is the ball. If you remember the concept of vapor pressure may define as the pressure exerted by the vapors of the component, pure component, on the top surface of the liquid or solid at VLE. Okay, so whenever, suppose this is the solid, its vapors must be there. Those vapors will exert some pressure, some force on this solid surface, and when these vapors and solid will be in equilibrium, so this pressure exerted by the vapors, it will be known as vapor pressure. So what happens actually, this solid ball will dissolve, the surface molecules of the solid ball will dissolve in air. So if you see the air, then here at point 1, the concentration of these solid molecules in air at this point 1 high, at this point 2 is low. So diffusion will occur now from this gas, in the gas, from this point to this point, high concentration to low concentration. Okay, so dissolution will occur and then diffusion will follow. Okay, so that's why here this PA1 will always be equal to its vapor pressure. So here, if you remember, the equation was Na bar is equal to Na over 4 pi r square, that is equal to dAb over RTR P over PBln, or you can write 1 over YBln, doesn't matter, times of PA1 minus PA2. I hope it is clear to all of you. That is the rate of mass transfer at any point in this radial distance, in this radial direction. If you want to see the flux or the mass transfer at the surface, so put R equal to R1. So flux upon area will be flux upon area is what? Sorry. I think it is Na and this is Na bar. Rate upon area is flux. So this will be Na1. If you put R equal to R2, this will be Na2. Yeah. So that's correct. Now this is Na bar, this is Na. I hope it is clear now to all of you. And here in this equation, here one thing which all of you should know, the time required for complete diffusion. If a spherical ball is getting diffused in air, then in how much time the total sphere will be diffused completely. So you can say Tf, that is the final time, is equal to rho A R2 square minus R1 square dAb PBln RT, dAb तो वहाँ नहीं आएगा, dAb will come in denominator. This is the equation. Okay, so they can ask the question complete diffusion. So in that case, complete diffusion, R1 will become 0, R2 will be equal to the total radius, initial total radius. Okay, and if they ask the question like this, we have a sphere of 5 centimeter radius, in how much time the radius will reduce to 1 centimeter. Okay, so this will be the R1, this will be the R2. That's how you can solve the problems related to time if they ask you. Is it clear? If complete evaporation is there, then R1 will be equal to 0. I hope it is clear to all of you guys. Okay. Similarly, suppose we have a beaker filled with liquid, for example, suppose liquid water or anything, and here we have air. then here they ask you the time required, or in how much time the total water will evaporate. So from this point, from the surface of air, this part, you can see the level is Z0 at time t equal to 0, this level, and at any point, at any time t, this level is ZF. Okay. So here the equation will be, you know the diffusion, the equation was Na equal to dAV over RT delta Z P over PBln PA1 minus PA2. Okay, this is the diffusion of A in gas. So here the equation will be rho A ZF square minus Z0 square RT PBln over 2 times of MA DAB P PA1 minus PA2. Okay. So if they are saying the total liquid evaporated, so ZF will be equal to the height of the liquid level and Z0 will be this. So here these ZF and Z0 are from this side. They are not from the base of the beaker. They are from the top of the beaker. Okay. The interface of beaker and air. These are the heights. So accordingly you can mention them. You can answer or you can put the values and calculate. And the last thing here is diffusivity or the diffusion coefficient. So remember this, DAB is inversely proportional to pressure for gases, and as we know that usually the liquids, the solids are incompressible, so they don't have the diffusivity of liquids, diffusivity of solids independent of pressure. Okay. And in terms of temperature, if you have to mention, so M will be equal to 1.5 for gases, 1 for liquids, and 0.5 for solids. So these things you should remember. Okay. So this is all about the diffusion topic here. So our mass transfer quick revision class lecture 1 was for the diffusion part. I hope we have covered all the topics from the diffusion and it was helpful for all of you to revise the entire diffusion chapter. Okay. Now there are some questions from GATE previous year papers. They have asked many questions from the diffusion in GATE previous year papers, but there are only few questions which we will discuss in the class. So I am sharing the questions with all of you. Okay. Try to solve them by yourself. See if you have any doubt. So tomorrow when we will be having the next class of mass transfer, we can discuss those questions. Okay. If you have doubts. Okay. So note down the questions. Okay. You can take the screenshots with you for now. So first is question number 17. This question. Question number 17. Okay. You can take the screenshot and try to solve it by yourself later on. Next is question number 3030 here. This one. After that we have this question number 72. This one. Then we have question number 100 for us to discuss. This question which we have already done. Question number 110. This type of a question they have asked almost 3 times in last 30 years if you see. 2 times in these 2 years. One 2015 and one was in 2004 or 2006 and one was in 90s. Similar question. Okay. So they repeat questions. And last one is this 118. Okay guys. So these are the few questions. So Dhrumil, I remember the question, that is I hope we have covered here. Okay, the question you were asking, the XC axis, that question was there. So we will discuss them tomorrow. Okay, so that's all for the day guys. In next class we are going to cover the topic interface mass transfer, convective mass transfer. Okay, where we will talk about the mass transfer coefficient, different forms of mass transfer coefficient, how we can remember those things, okay, equations. And if you have any doubt in those topics, so obviously we can discuss. So these questions you guys can try to solve by yourself. If you will be having any doubt, we will discuss tomorrow. Okay, so that's all for the day guys. I hope this class was helpful for all of you. See you in the next class. Stay safe, stay healthy. Bye bye, take care. Tada. See you tomorrow at the same time.